We are now going to introduce various kinds of rates, namely discretely and continuously compounded forward rates and spot rates. We will also consider various approaches to modeling the term structure via stochastic dynamics, for example, short rate modeling, bond price modeling, and forward rate modeling. In addition, we will look at the relationships between these different ways of modeling. For example, how to translate from forward rate dynamics to short rate dynamics, or from a zero coupon bond price dynamics to forward rate dynamics, etc. Now the last three slides of this section contain some tedious but straightforward calculations which depend on the Ito formula as well as on changing the order of integration as taught for example in second year calculus courses, and I will leave these to read on your own. Recall that our basic instrument is the T-bond, i.e. a zero coupon bond which pays 1 unit of currency at its maturity, capital T. Now consider a trading strategy where we trade at 3 times, namely little t, capital S, and capital T, as shown. At time little t, we short an S bond, which leads to a cash inflow of PTS. We use this cash to buy as many T bonds as we can, in other words PTS over PTT many T bonds, and this means that we have a net cash flow of 0 at time little t. Now at time capital S, we have to redeem the S bond that we are short, in other words we have to pay 1 unit of currency. Then, at time capital T, we will receive 1 unit of currency for each of the T bonds that we own, in other words we will earn PTS over PTT many units of currency. So at time t, at zero cost, we can implement a strategy that requires us to pay 1 unit of currency at time capital S, and which will grow to a payoff of PTS over PTT at time capital T. Now this looks like we make a deposit of 1 at time S, which grows to PTS over PTT at time capital T, and this applies a discretely compounded rate of capital R over that period. Equivalently, it could imply a continuously compounded rate of capital R as follows. Here the two R's are different and they're called forward rates. So let's just go over that one more time. We have a trading strategy enacted at time little t, where we trade at the 3 times shown here. At time little t, we shorted an S bond and we used the proceeds to buy PTS over PTT many T bonds, so that the net cash flow at time little t is 0. At time S, we have to pay 1 unit of currency to redeem the S bond, and at time capital T, we receive PTS over PTT from the maturing T bonds. So at time little t, we can set up, at zero cost, a strategy that allows us to deposit or pay 1 unit of currency at time S, and which will then grow to PTS over PTT at time capital T. And this implies an interest rate, the forward rate, for the period from S to T, but this interest rate is locked in at the earlier time little t. So for continuously compounded forward rates, we would have that e to the r times t minus s is equal to PTS over PTT, and this implies a continuously compounded forward rate as follows. Or equivalently, if we wanted to use simple rates or LIBOR forward rates, we'd get the following expression, which we can solve for L as follows. The continuously compounded and simple spot rates at time little t are the forward rates starting right now, i.e. starting at capital S is equal to little t. Thus the continuously compounded spot rate, RTT, is given as follows, where on the right hand side we have the forward rate. And similarly, the discretely compounded spot rate is given as follows. The instantaneous forward rate, FTT, is the continuously compounded forward rate for an infinitesimal period. This is why it's called instantaneous. In other words, the instantaneous forward rate is given by the limit as delta t goes to 0 of the continuously compounded forward rate for the period from t to t plus delta t. If we plug this into the definition, we see that we obtain precisely the negative of the partial derivative of the logarithm of the zero coupon bond price with respect to its maturity. This is why we require the bond price to be smooth as a function of its maturity. Now observe that if t is less than capital S is less than capital T, then the integral of the forward rate is simply the integral of the derivative of the logarithm of the bond price, which by the fundamental theorem of calculus is just the logarithm of the bond price evaluated at the two limits of the integral. Rearranging, we get the following expressions for bond prices in terms of forward rates. Notice here that this expression shows that the spot rate from the period from little t to capital T is precisely the average forward rate over that period. It remains to define the short rate, which is the instantaneous spot rate, i.e. the instantaneous forward rate starting right now. RT is equal to FTT. Associated with the short rate is the riskless bank account or the money market account. Next, we look at modeling the term structure. In particular, we will discuss the relationships between three methods for modeling the bond market. The first method is to provide short rate dynamics. In other words, we provide a drift A and a volatility B for the short rate R that we've just defined. Alternatively, we could provide zero coupon bond price dynamics in the following form, where we have a drift of M and a volatility of V. And finally, we could provide instantaneous forward rate dynamics of the following form. We have a drift of alpha and a volatility of sigma. Note that in the second and the third case, we have actually infinitely many stochastic differential equations, one for every maturity capital T. Here the Brownian motions would also be multidimensional. For short rate dynamics, we typically use a one-dimensional Brownian motion. Moreover, typically we do not actually specify zero coupon bond price dynamics, but for the pricing of bond options, it is important to know how to derive bond price dynamics from short rate dynamics or instantaneous forward rate dynamics. Hence, it's important to know how to transform between these different ways of specifying term structure dynamics. Here are the various relationships. If bond price dynamics are specified as follows, with a drift M and a volatility V, then instantaneous forward rate dynamics will be specified as follows, with a drift alpha, which depends on the volatility and the drift of the bond, and a volatility sigma, which depends on the volatility of the bond. Here the subscript capital T, seen here, here, and here, means the partial derivative with respect to the maturity, capital T. Similarly, if instantaneous forward rate dynamics are specified as follows, then the instantaneous short rate dynamics are given like this, where the drift A of the short rate is obtained as follows. Again, this is the partial derivative with respect to the maturity variable, in other words the second variable, and B is specified as follows. And finally, if the instantaneous forward rate dynamics are specified like this, then bond price dynamics look as follows, where R is the instantaneous short rate, and capital A and capital S are obtained by integrating the instantaneous forward rate, drift, and volatilities respectively. This latter form here will be important when we derive the so-called Heath-Jarrell-Morton drift conditions. In order to prove these relationships, we need some preliminary results. Firstly, here is a Fubini's theorem for stochastic integrals, which simply says that we can interchange the order of integration even if we're dealing with a standard Lebesgue integral, i.e. an integral with respect to Lebesgue measure, and a stochastic integral, i.e. an integral with respect to Brownian motion. This interchange of Lebesgue and stochastic integral will hold subject to some conditions shown here. We omit the proof, which can be found, for example, in this paper here. We also need some results about differentiating integrals. In the first box, we just have derivatives of standard Lebesgue integrals, or Riemann integrals. The first theorem here is just one way of phrasing the ordinary fundamental theorem of calculus, and the second and third follow from it using the Fubini theorem and the chain rule, and these are left as exercises. The second result shows that we can differentiate under the integral sign. And the proposition at the bottom here shows that we have a similar result for the derivative of a stochastic integral. This is also left as an exercise and requires the stochastic Fubini theorem. You're now ready to tackle the proof of the relationships shown on this earlier slide here. These can be found on the following 3 slides, and it is left to you to check that these derivations are valid.